So if you'd like to learn some stuff with me, then go ahead and follow along on those, or you can start joining us on live. And then the bonus of the live thing is you can actually ask me questions, of course, because this is for you guys. It's not for a class. So if anybody has any questions, they can just ask at any time. And if I can't get to them during the discussion series, then I will answer them after. So let's begin part 4 of electricity and magnetism. Again, if you are watching on Twitch, !Discord, my notes I always put into the Discord so you can follow along so that you don't have to take any of your own notes and you can still have something in front of you if you want. And if you are on YouTube, all of that information is down in the description. But anyways, let's begin. So we have E and M part 4. And we always start with the last time. Ooh, am I in the frame? I did not check that. So last time we talked all about potential. So so we had two things really we wanted to be able to use. We wanted to solve the electric potential in two ways, right? The first one was the electric field is equal to the negative divergence of the potential, which means, or gradient of the potential, yeah, which means that we just take the derivative of it in a certain way such that we could get the of the potential. And then the way that we did it was usually we did it backwards. The potential is equal to the integral of the electric field, yada yada. I am barely in frame. As long as I am in frame, I think it's good. Things look good. Yes. Okay. So we did it that way where and then the point of this was we knew the electric field because we solved for Gauss's law, right? So we started with the electric field by solving it for Gauss's law, and then we were able to take the derivative or take the integral of that in order to find the potential. The second way that we found the potential was to set up the formula for a point charge. So if we had some point charge, and this is the one that you might be more comfortable with seeing if you are, in the intro physics class, or if you've just taken the intro physics class or whatnot, because this is the one that we start with in that one, where we'll have some charge Q and then some point of interest P and some distance between the two. We'll call that crazy R. And the formula that we just sort of give the intro physics students is just V of R is equal to 1 over 4 pi epsilon naught times Q over crazy R. Right? And then this is the potential for a single charge. Now, of course, we extrapolated this into many charges. Like, instead of having a single charge here, what if we have a bunch of charges and we want to find the potential of the collective group of charges? Well, that just follows the laws of superposition, right? So it follows the laws of superposition. And because of that, which means we can just add all of the different contributions together to get the total. Now, because it follows the laws of superposition, we can figure out, oh wait, there's not 3. This is still second one. We can extrapolate this into some shape by using calculus. Namely, if we have some shape, so just pick some arbitrary shape, we have a point of interest P out here, we can take a infinitesimally, oops, that's supposed to be a straight line, an infinitesimally small chunk of this called d tau, and treat it exactly like a point particle. That's the benefit of taking an infinitesimally small piece, okay? Can you guys see everything all right? Yeah, that looks okay. It's d tau. Yeah, so you could take an infinitesimally small piece and treat it like a particle, and then you can get a new formula where you take advantage of something namely the uniform charge density. There is some limitations to this. Oops. We have the integral of dq over crazy r. Now, we had to take this dq and we used the charge density. Hi, Alphinator. Good to see you. Good to see you. How are you today? But we took this charge density, or we took the advantage of this of the charge density to figure out what this dq is, because usually you don't integrate over charges, usually you integrate over space. So integrating over space is more, it's easier and more attainable than integrating over a charge. So again, we have to take advantage of that charge density. Now, this was what we did last time. Okay, is we just found the potential using 2 ways. But there's going to be more. Now, if we're going to skip pages in Griffiths, and mainly because it's about boundary conditions, and we're going to be learning a ton about boundary conditions in chapters 3 and 4 when we start to go over potentials a lot more. We start to do Laplace and Poisson's equation in like real situations, then we're going to need boundary conditions to be like on point. So we're going to talk about it a lot then. So we'll either just go back to it. The name of the book is Introduction to Electrodynamics by Griffiths. David Griffiths. It's pretty standard in school that you would do that one for your undergraduate electricity and magnetism for your physics degree. There's another version that looks like this. All the page numbers that I give you will be based off the blue book, and the black and orange book has different page numbers. But they are the same book. Yes, Ash. So the pages that we're skipping are 88 to 90, and we're going to pick back up on 91. Work and energy and electrostatics. That's where we're starting today with the new material. Okay, so let's go ahead and do that. So we're doing work, and energy in electrostatics. Now, the nice thing about, well, we're going to see something kind of cool come out of this. And like I say this, it's kind of cool because I've taught intro E&M a bunch of times now. So, you know, as a TA. So this is kind of cool because like you're never really taught that this is where it comes out of. But here we are, and I'm going to teach you where these certain formulas come out of that seem a little bit like, I don't know, ad hoc maybe in your intro physics class. Okay, so if we have a bunch of charges, okay, and I want to take a charge right here and move it from point A to point B. So I'm going to take a charge and move it down here. We want to know what work is required for that motion. Okay. Now I can talk about the forces, right? Laws of superposition and everything. The force on this particle of all of these, we just add up the forces of each individual one. But you can kind of generalize it to the force total is equal to the charge of this particle, which we'll say Q, times the electric field of each of the particles, you know, as the total electric field from each individual contribution. Now, this is what we did like the first week, right? And so if we act on this particle, so this is how much we get. So in order to get a motion, we should act on this particle with just the opposite charge, or the opposite force, right? Then the force is constant, and we can actually move it freely by acting on it with a force equal to that. Okay. So if we want to talk about work, of course, remember the equation for work. Work is equal to the integral of from A to B of the force with the dotted with the line integral. Okay, or the line, excuse me, DL, the line segment, the infinitesimal line segment, which would just be like splitting one of this little bit right here, DL. And then we're going to integrate that to the whole line, and that's how we get the work done. Now, what's the force? Well, force, of course, we have. Force, of course, is a horse, of course. Is, given by this. So this is the force we have to apply to do that work. So this is going to be minus Q times the integral from A to B of the E field dotted with dl. And then we can just say that this is going to be, then we can evaluate this integral. And this, of course, is going to be what we did last week, which is negative, or this is negative EDL. It's just going to be the potential. So it's going to be the potential evaluated at these points. So Q times the potential at B minus the potential at A. Just the potential difference is really what we're doing here, okay? So here, note again that this path is independent. Like, this is the cool thing about this is this is the path's independent. So it doesn't matter if we took this path or if we took a path that was like wee or like wee, like lightning bolts. Doesn't matter. Path independent. Okay. The nice part is that it's always the same thing. Okay. Yeah, we built the Tesla coil. It took us like 3 weeks to build it because there was a lot of issues I ran into, but we did end up building it. I have a couple clips in the videos section on here. You can take a look at the Tesla coil if you're interested. Okay. So if we rearrange this, we can just rearrange it in the following way. And namely, if you see on the notes, can I skip that step? No, I shouldn't skip that step. So if you look in the notes, so I'm not going to skip it. We'll rearrange it to look like the potential difference on this side is equal to the work times Q. But then you can do something else, right? Like we talked last time about what's it mean to move the point of origin, right, from where we're considering it. And we found out that when the potential difference, we're talking about the potential difference, the moving the point of origin doesn't have an effect, okay? So let's do this. Instead of just picking, A and B, let's say I want to take a group of particles like this one, and I want to bring a particle in from infinity and get it into the mix somewhere like right here, okay? So I'm going to take a particle and bring it from infinity into there. Well, what is the potential difference then? Well, we've already seen that the potential difference at infinity is going to be 0, okay? Or the potential at infinity is 0. So if we have one of these at 0 and the other one is just at some radius away, so if this is the group, and this is some radius away, then what we can say is, if I can find it, so that the work is just going to simply equal the charge times the potential of the particle. Well, let's bracket that off. But then the potential of the particle away. Now this is a curious formula. Okay? So if we have some charge Q here, okay, now it's a different one, and we're bringing it into the mix, right? If you want to consider the potential of all of these particles on this one potential, you're just bringing this in from infinity, right? So it just turns out that it's the work of that particle is Q times the potential. Does anybody know where they've seen that before? So the minus right here, by definition, it's V is equal to the negative integral of E dot dl. So I'm going to eat this minus up right here. When I plug in this V, I'm going to get minus there. Does anyone remember where from intro intro E&M they might have seen something similar to this? While I erase this, I'll give you guys a second to think about it. Usually we talk about it as electric potential energy. Like a lot of times we'll see this as U, right? Well, we'll just have some, let me write it out so you guys might be able to see something that looks similar because we're going to need it in a second. Sometimes you might see it look like this. QQ over 4 pi epsilon naught R, right? Where this R is the difference between these two Q's. So ironically, or maybe not ironically, it's similar to Coulomb's law. Coulomb's law is usually the force one, but it's similar in that sense, right? The force, and usually this comparison is drawn a lot in Introduction to Physics. Yeah, you have the inversely proportional versus the inverse square proportionality. Kelly Voicer, welcome to the channel. Thank you for the follow. So there's that. So this is the Coulomb's law, but usually we draw the very good distinction. So that was really good that you recognized this. And that was it's a nice comparison because then you can do the E field. Versus is Q over 4 pi. I'll just do the distinctions really quickly and then the V is just going to be Q over 4 pi epsilon naught R. So they kind of show up as like different rules. One's associated with the inverse square law, and one's associated with the inverse law. So that's potential energy. So let's move on to the next section, the energy of a point charge distribution. So how much work is required to assemble many charges, right? So is this going to be the same thing or is this going to be different? So let's see. So what if we wanted to do many charges? We wanted how much work is required to assemble a lot of charges. So let's just start with one. So we have one Q1. Now obviously there's no electric field, so there's no work. Okay, no electric field, no work. So we're just going to move in Q1 from infinity. Okay, that's the point, is to bring it in from infinity. So we're going to bring in Q1 from infinity, no work. Okay, so now we have Now we have Q1 here, but we're going to bring in Q2. What's that one? Well, that's just two particles, so that's not bad. We're going to utilize our formula as it is up here, and we'll get that the work is equal to 1 over 4 pi epsilon naught times Q2 times Q1 over crazy R12. Okay? Now, if you want to take Q1 and Q2 and bring in a Q3 out from infinity, and now we're going to have you're going to have two radii, right? One radius here is 1, 3, the difference between particle 1 and particle 3, and then this one's going to be crazy R 2, 3, the difference between particle 2 and particle 3. So we're going to bring in 3 out of infinity, and what are we going to get? Let's label this work 2, work 3. I actually have a... Yeah, well, we'll address that when we get to it. So then work 3 is going to be 1 over 4 pi epsilon naught. Q3 times Q1 over R13 plus Q2 over crazy R23. No field, no work. Nice. Get it? Like they're on strike. Okay, and we can subsequently just bring in a fourth particle, and it is exactly what you'd expect. Let me just write it all out, because then we're going to simplify it, get kind of a generalized form of it. But it's going to be Q4 times exactly what you think. Q1 R14 plus Q2 R24 plus Q3 crazy R34. Okay, so very good. Now we have the work of the 3 particles. Now we get to write out what all of them are combined. I used the word superposition. I may regret that, because there's some weird things going on with superposition here. Superposition might have been the incorrect word to use. But let's keep going, and then I'll decide later if I think that was the wrong word to use. If anything, it's just grammatics of it, I think, might just be incorrect. Because we can add up all of the works to find the total work, but that doesn't necessarily mean that it's a superposition of the work with the individual particles. So let's add them all up to get the total amount of work. So we'll do work total, 4 pi epsilon naught, of having all of these particles, pretty much starting with Q1 and then adding 1 in at a time. What do we get? Well, we get what you think. Q1, Q2 plus crazy R12. Q1, Q3, crazy R13 plus Q1, Q4, crazy R14 plus Q2, Q3, crazy R23. Let's go down here. Plus Q2, Q4 plus crazy R24. And then lastly, plus Q3, Q4, crazy R34. Okay, so now we can see the entire thing drawn out, and we can generalize exactly what's going on. Every time you add in a particle, you have to add the work done with every single one of those particles. So we can write a generalized formula that looks like this, and I'm going to and the reason I wrote this all out, it seems a little bit much, but I want to kind of make sure you guys can see this in the generalized formula. So if we have the summation from I equals 1 to n, then we'll have one way to write it would be j greater than I to n, and that's going to be from qi, qj over crazy rij. Now look at this one. This one's kind of nice, right? We just get this out in front, and this j greater than I controls how much we get. Every time we brought one in, we're adding up this I with this j attached to it, okay? And that just means that it's going to be in ascending order. So we have 1, 3, 1, 1, 2, 1, 3, 1, 4. And then I hits 2. What's higher than 2? 2, 3, 2, 4. And then I hits 3. What's higher than 3? 4. Okay? So it works like that. Is the superposition the right word to use? Is that what you're meaning, Alphinator? It's the most tough book as I came across the entrance in India. Interesting. Cool. So that's the way that this works. Now there's another way you can write it. And that is 1 over 8 pi epsilon naught. Excuse me for the rubbing of the microphone. And that's going to be the sum over I equals 1 to n, sum over j not equal to 1, or not equal to I, to n. Now this is the big difference between this. Oh, and let me write it's the last little bit stays the same. qj over crazy rij. Now this is kind of nice because now we have j not equal to I, but doesn't necessarily mean to be greater than. What's going to happen if we try, so is that or? What's going to happen if we try to count it up this way, where we have it like this? We're going to get double count. That's what's going to end up happening. The 8 takes care of that. Okay? Welcome to the channel. That's what's nice about this. Weird. Eugen nerd. Did I say that right? Eugen nerd. Eugen nerd. Thank you for the follow. Welcome, welcome, welcome. Yeah, so I don't know if so let me know if I said that right, Eugen nerd. And then this basically it. Like, we're going to double count. So instead of having 1, 2, 1, 3, 1, 4, we're going to have everything. So when you get to here, instead of going 2, 3, 2, 4, you're going to get 2, 1, 2, 3, 2, 4. And of course they're not equal, so you won't ever see 2, 2 or 1, 1. But that's the point, is you're going to get a 1, 2, and you're going to get 2, 1. So then you just divide by 2 and you get rid of half of the entrance. The electron is in Uber space. Thank you, Eugen nerd. The question was just what happens if we add up with j not equal to I? So what happens if we add up with j not equal to I as opposed to j greater than I? The difference between the two. And the difference between the two is this one we're just double counting. Okay? But there's a benefit to this. Namely that we can pull out qi in the following way. So we'll have works equal to 1/2 times the sum over all qi. I equals 1 times, inside the parentheses, we're going to have n to the I not equal to j, 1 over 4 pi epsilon naught, times q, j, crazy r, ij. Now, I kind of let's box that off. I kind of ran it into this one a little bit. Okay, now what's special about this? Well, what's special about this is just the potential. This is the superposition of the potential. So look at, this is just all of the potential, the total potential at this particle, right? We've been doing this. We've been talking about this, right? If you just take all of the potentials added up, you just get that right-hand side right here, okay? So let's rewrite that. Actually, no, let's rewrite it over here. Get too cramped over there. Too cramped. A lot of equations today. Interesting potential stuff. This lesson has a lot of potential. Okay. Work is equal to 1/2 the sum over I equals 1 to n of qi, just times the potential of all of the particles at some radius I away. That's it. Easy breezy. Okay? And then there's just a note that Griffiths makes that I think is very important. The amount of work needed to assemble this configuration is also the amount of work needed to disassemble it. Now, there's a lot in this. Good one. Now, there's a lot in this book leading up or after this that's about like it's about in this section, namely, about like the negative signs and whatnot. And he wants to emphasize that the negative signs are all taken care of with that little fact. The fact is that the amount of work needed to assemble the configuration is the amount of work needed to disassemble. And that means it's representative of all of the energy stored. Okay? Can I be infinite and J be infinite? Plus 1, is it possible? You will see what we're going to do, and you will see that right now. What happens if it's continuous charge symmetry, okay? What happens? It was a great leading question. It's almost like we planned this, Parzival. But this is the nice thing. What if we have a continuous charge distribution or a continuous charge symmetry? Okay, so again, now think about if we have some volume with the charge density. Now it's a volume. Very, very important that it's a volume. Why is that relevant to what Parzival said? Well, actually, we can take a chunk out of this like we did last time, d tau, and now we have an infinitesimally small chunk. And we're going to treat that like a point particle. So what does that mean, and why is that relevant to Parzival? Well, if there's an infinitesimally small chunk there, that means we can add up infinitely many of these, right, in that section. And how do we do that? Using the tools that we know. Calculus. 1/2 the interval of the charge density times the potential times the infinitesimally small charge section. So now we have a volume charge density, but bear in mind we don't necessarily need to use volume. We can use area or length as well. And both of those, remember, the only difference between the three different dimensional objects is just the rho d tau versus sigma dA versus lambda dL. Sigma being the area, charge density, and lambda being the length charge density. Now, where are we? Now we're going to do a little bit of tomfoolery, a little ballyhoo. And what we're going to do is some integration by parts. Oh, before we do that, we need to actually lay out what we're integrating by parts. So how do we evaluate this? Well, remember that the divergence of E is equal to the rho over epsilon naught. That was Maxwell's first law that we derived the first week of doing this. Yeah, we're very similar to that. We're going to do something very, very similar to that. I'm not actually going to do the evaluation. It's in the beginning of Griffiths in chapter 1. But I'm going to show you the formula he uses to split it up into something pretty similar to what you're talking about. So if we were to rewrite this now with our gradient of E, we get the work is equal to epsilon naught over 2 times the integral divergence of E times the potential times the infinitesimal small volume. Now, this isn't as pretty. We don't like this too much. So let's use our little, like I said, our tomfoolery, our ballyhoo, and split this integral up using integration by parts. So I'm going to give you the formula. He derives this in the beginning. If anybody would like to see that, we can definitely do that at some point. I just have to go over it really quickly. But here we have some integral that looks just like this one, okay? And now we want to change it. The only difference is the scalar is here versus here, but it doesn't matter. We can just move them around. Because, of course, the divergence of E is also a scalar, so everything commutes in classical. And we get the negative the derivative, or negative the integral of A dotted with the divergence of the scalar, d tau, plus the surface integral of the scalar times the vector dotted with dA. Ooh, what do we have here? Gathwaggle. Where were we? Yes, integration by parts. We're going to split this up because we don't really want this divergence on the E field. And we're going to get this. Now, what happens if we split it up? Well, let me show you what ours looks like. So the work now is going to be equal to epsilon naught over 2 times the quantity of minus the integral vector E times the gradient. No, stop this. Divergence, excuse me, of V, gradient, divergence, whatever. You guys know them. It's gradient. Plus the surface integral. Now this is a volume integral. This is a surface integral. That's going to be very important. V E dot dA. There we go. And here we go. So that's the new one after we do this tomfoolery. Okay, now this is kind of interesting because we have a volume integral here and a surface integral here, but they don't behave the same. Oh, first we should remind you that Of course, we talked about this. Divergence of E is equal to, or the divergence of V is equal to minus E. So what happens here? Well, that is going to be nice because then we just get epsilon naught over 2 times minus the volume integral of E squared. No more vectors now. Constant, or scalar, plus the surface integral of V E dot dA. Now, here's the tricky part. This is very, very tricky. Okay? What volume are we integrating over? But we are. That Russian guy. Perfect. Perfect, perfect. We're integrating over the universe. Why are we integrating over the universe? Well, here's the trick, okay? This one, this dt, it lives here. It lives in the d tau versus the dA. The d tau is not going to have a dr in a spherical situation, right? In a spherical thing. So in this one, will though, right? It doesn't depend on the radius. This integral does not depend on the radius. The radius is a constant. So as it gets larger, as this integral gets larger, like if we just had some shape, right? Like some shape, and we were to draw a volume around it like this. A little bit weird. Thank you, Anifer, for the follow. Sorry if I said your name wrong. I feel like I've been doing that a lot lately. So if we have a volume right here, some volume with charge density, and we were to draw a sphere around it, right? The surface charge density is just going to get bigger and bigger. As we make the sphere bigger and bigger, the surface is going to get bigger and bigger, but it's not going to be, we're not going to be changing it as an integral of r. So the r is not going to change. So as we get out to infinity, this r is going to change as far as how big it goes, but nothing else is going to change in here, whereas this is going to be integrated over. So that means as we get bigger and bigger with the volume density, then this is going to kind of take over, and this one's eventually going to go to 0 if we use the size of the size of the internet. If we use the size of the universe. Are you confused? So was I. When we get to an example, I think you'll understand. So if you are confused with that, hang on. Now, so we're integrating over the volume of the universe. So that means that this one will effectively go to 0. And really, we only care about this integral right here. E squared d tau over all space. Now, of course, you don't have to do all space. You can just pick some finite region, but then you want to include both of those. Let's keep, we're almost done. The only thing we have left to do is the example, and then we'll call it wraps for the day on this E&M, and we'll move on to our next segment, which is about, I want to hear about how you organize your research, your school, your life. We've already had a couple cool ideas that I want to look into with you guys. Okay, so example. Now I'm not gonna write the whole example, but you can follow along on Discord with my notes. Also join the Discord server. Looking forward to chat with other undergrads. Awesome. Cheers from Italy. Cool, cool, cool. Well, good to have you. And the Discord's a great place to ask questions and chat with other physics students and other physics enthusiasts, definitely. All right, so if you're in Discord and you have the notes, you can just follow along. I'm going to read it. Find the energy of a uniformly charged spherical shell of total charge Q and radius R. Remember, we've did this before. We did this twice last week when we tried to find the potential away from the spherical shell. And because of that, we know a couple things about it, right? So if we were to say, solution 1, we're going to start by utilizing the work equation, 1/2 the integral. Now we're on a shell, so we have to make sure we use the appropriate charge density, which is an area charge density. Potential on the surface of the shell is constant. Remember, we did that last week. We found that the potential on the surface of the shell was constant, and inside the shell, it was constant as well. And then, therefore, we can just substitute this, we can substitute this potential inside, and we get 1/8 pi epsilon naught Q R times the integral of sigma dA. This is, of course, what? This is, of course. Sure thing, Admiral. This is, of course, the, this is just the charge, right? Because we have the integral of dq is equal to the integral of sigma dA So we just do the integral of both sides, and we can even talk about the integral over the whole thing is really what we should be talking about. So then this would be total Q is equal to sigma total A, which is good because sigma should equal QT over AT, right? And that's good, 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 good. So now this then becomes 1 over 8 pi epsilon naught Q squared over R, okay? And this is just set up in a way that it's where the total charge is equal to that. I didn't make it as clear as Griffiths makes it in this example. So this is example 2.9 if you're following along, by the way. Okay, so let's keep going. There's solution 2 we have to consider. Solution 2 has a bit of different approach to it. Now, inside the electric field, or inside the sphere, the electric field is 0. We talked about that quite a bit. Inside the sphere, the electric field is 0, but the potential is not, but that's not important right now because really what we want to talk about is the electric field. So if the electric field on the outside is 1 over 4 pi epsilon naught, this is the approach where we talk about the electric field and use that work integral that we had before. Q over R squared R hat. Now if we just take E squared is going to equal Q squared over 4 pi epsilon naught quantity squared times R to the 4th. Now our work total is going to equal epsilon naught times 2 times quantity 4 pi epsilon squared. Now again, I'm just doing the E squared on the inside. So Q squared over 4, or yeah, R to the 4th times, and here's where we get the rest of it. R squared sine theta dr d theta d phi. And this is what I was talking about. If you just have the surface integral, then you're not integrating over dr. The real bounds of this, let's write it out. 1 over 32 pi squared epsilon naught times Q squared times 4 pi. Of course, this 4 pi coming from the solid angle, which is the double integral of sine theta d theta d phi. Okay, so that's a double integral, and that just is the solid angle theorem. It always equals 4 pi as long as it's going from 0 to pi in theta and 0 to 2 pi in phi. So we always have that for a sphere, especially in this book. And then the integral bounds are from R to infinity because we're going to be coming in from infinity. R squared dr. Now this is the point. This integral, this was the one where we had 1/2 the integral of e squared dt, right? D tau. I think this was epsilon, not 2. Let me double check that. Yes. So this was this integral, right? And remember, we had the surface integral, but notice how if we just set the outside of the surface to infinity, then that one goes away. 1 over infinity is 0, and now we have this one, which changes. We're integrating from R to infinity. So while this bound may go into infinity, this one does not. So we end up getting a real value of 1 over 8 pi epsilon naught Q squared over R. And is it the same thing? It is. So that's the trick. That's why if we set this volume to infinity, then the other term goes to infinity, but this one does not because we have one term at infinity but one term at R. So it actually salvages itself and comes out. And we get a real value. Anyways, what do you guys think about that? That is E&M part 4. Just showing, I think it's really kind of crazy how we actually say, like, we're going to take the integral over the entire universe. And if we do that, then the half of that doesn't even matter. But it's perfectly fine. It works perfectly well. I mean, it's really just taking advantage of the fact that we can integrate over the entire universe for a small section. Even if it's this, even if it's microscopically small, it doesn't matter. It doesn't actually contribute to anything.